everything we've done in lesson 1 and 2 has led up to this definite integral. Just to remind you, lesson 1, we had these strange shapes, and we approximated the area by maybe finding 1, 2, 3, 4, 5, 6 rectangles, and maybe you wanted to do the midpoint. So I do the middle of it, I go up to the function, I cross over to make the same, that rectangle. Go to the midpoint, go up to the function, cross over till I get to the other one, I'm off. Midpoint, you got the idea. We approximated it with rectangles. The more we did, the better. Then lesson 2 was just madness. Lesson 2 said that we start with a function, and what we did was break it up into hairline rectangles. There's thousands and millions of them, and tried a whole bunch of them, and count them was basically if this was 0 to 7, then my width of each rectangle would have been, I call that delta x, is 7 minus 0 divided by n. Then we went and wrote our limit as n goes to infinity of the sum of k going from 1 to n. And then we created some sort of formula for the length and the width. Well, the width was 7 over n. That one's not hard. The length had to do with the function that I reached to the top. Even when I was doing a big rectangle, I had to figure out, well, where did I touch the rectangle at? So that was f, and we were actually doing whatever that function was, we were plugging in the k in place of the x. And that was a lot of work. It took us that whole page, and I'm going to do a couple more, I think, just to give you guys, maybe when you over the weekend, you'll see maybe 4 more that are completely done. Maybe I'll take them from the homework to help you out off of that lesson, because you had, let's see, back up here. Yeah, you had, those are summation problems. Let's see, where was limits of finite sums? Well, those were just sum. Where did I give you some that are find the area? Huh. I didn't make you find any areas on that homework. Thought I did. Then I dropped the ball if I didn't give you, huh. Was there a third page? I probably messed up. I need to give you a couple of those, but I'll worry about that later. So let's go into the depth. Oh, all of this led to the sigma being the integral. So area, this also gave you area is the exact answer. This gave me area is approximate answer. The sigma from A to B of your f of x is all you had to do is integrate from A to B, and that gives you the exact answer as well. So what I would do, since today's lesson is definitely all about this, it's not about the rectangles anymore. This is important for AP. This is the rest of the story of where this came from. So start it right away. Some of this stuff in our book is kind of complicated how they wrote it, so I might skim over some things. In this section, we consider the limit of general Riemann sums. When you cut up oh, I got people in the, see, if I don't, people are late, then I end up not knowing you're in there. When we cut up a figure, when you cut up a figure into pieces, it doesn't even matter. You could actually be doing trapezoids, which is kind of interesting. You could actually got this shape here, and you're going up, and you could actually go make it into trapezoids. There is, because trapezoid just means one side well, I guess I'm making rectangles by default. That's Riemann sum. Riemann, because the guy name was Riemann. And he developed that you could approximate an area by cutting it up into pieces. Doesn't matter if you cut it up into rectangles or triangles or trapezoids even. But this is basically giving you the theory behind that summation and becoming the limit of the sum. And that's what we were doing in the other lessons. But this is what we like because it's easy to do. This gobbledygook is pretty hard. Okay, it is hard. This is the calculus that the AP wants you to do for sure. So we've already talked about the integral sign from a to b of a function d of x. They're acting like this might be the first time you ever saw it, but because I remember when we did the 1 minus x squared dx from 0 to 1, I wanted to see what the answer was. So we just do the antiderivative of this piece here, and that should be x minus x3 over 3. And all of this goes from 0 to 1, and that's my upper limit, that's my lower limit. Just think about it when you're going from left to right. 0, well, you're going to find out today's lesson, you could reverse those, but then you got to make a switch. So when I plug in my 1, I get 1 minus 1 cubed over 3, minus, and you plug in the lower limit, that gives me 0 minus 0 cubed over 3. That gives me 1 minus 1/3, which is my exact answer of 2/3. Because even the computer, when they did a chart for how many rectangles, it was approaching 0.6666, if you recall. And that is 2/3. So this is so much easier, even though it's considered advanced calculus, it's so much easier than doing the limit of the sums, which I may have to modify that homework assignment in the textbook if I didn't put any actual do it. You need to do a couple.
I'm sorry.
Yeah.
So for the last one, you said you found the antiderivative and you subtracted by the limit.
Oh, this one right here?
Mm-hmm.
I did the antiderivative right here. There's my antiderivative. But I'm going from 0 to 1. So usually we just put a bar and we put 0 to 1. We take the top, I plug it into my antiderivative. Then it's very important after you plug it into the antiderivative, you have to subtract plugging in the bottom one. It just so happened my bottom came out to 0. 0 minus 0 cubed is 0. So really this was my answer. I got lucky. 1 minus 1/3 was 2/3. And that is the exact answer for the area under this, that curve that we were working on, if you remember, was the upside down parabola. We did it from 0 to 1, and we did it with rectangles, remember? A lot of rectangles. Then we did it with the limit of the sum. That was that last problem that I did for you guys, and it took up the whole page. I hope you do it again just to practice it. Is it the end of the world if you're not a professional at figuring out how to do all those thousands of rectangles? No, it's not, because in the AP test it's not there, but it is expected in college that you understand it. Uh, I'm not even going to talk about A plus K. Yeah, I'm not going to talk about this particular derivation. It's gobbledygook. Uh, when we do this, it's important that you understand that the function that we're integrating is continuous from A to B. That's very important. You can't have any gaps in there because then you can't integrate if there's a hole. I mean, just use some logic here. If I decided to do this function here, and that one's okay, but what if it was a rational and it did that, and there's an asymptote here? You'd have a hard time integrating from 0 to 10 if there's no continuity here. So we're always talking about being continuous. If a function f is continuous over the whole interval from a to b, so if this is my a and this is b, I can't use this integration. If this was a and b was here, then I could, because then I would have this region here, right? And that would be legal. That would be continuous from a to b. But if b was out here, I couldn't do it. And it also has that f has at most finitely many jump. What is that? If f has at most finitely, not infinitely, many jump discontinuities, then the definite integral of a of b of fx exists, and f is integratable. Okay, so we don't want the jumps. Why is there a blank page? I hope I have the right file. Did your notes have a blank page after this? No comment. Is there anybody there besides Claudia? She talked.
Sir, I don't know if there's a blank page.
You don't have the file open?
No.
Oh, well, that's honest. Let me let me look at the one that I uploaded. Because I just noticed that I didn't put up the one that had the homework on this one. And I don't have it in my OneDrive, but I might have put it in It's Learning. So I got to check the It's Learning and see. Oh, I remember something. I remember I put even the PowerPoint in It's Learning. I don't know why. I don't know
My
why.
blank page.
It's blank?
Yes.
Okay. Then I'll just go on. So that's the next page, was just these properties. Uh, I had more. I had something else there, but I think I'm missing something. Here's the definition. If notice he's not going from, normally we do this. We integrate from a to b. A is typically from left to right, and so left to right, a will always be smaller than b. And that's how we do our integration. We always go from left to right. But if for some reason you switch it up and I want to go from B to A and I want to go the other direction, it changes the sign of the answer. Okay? I can prove it to you here. If I'm integrating from 1 to 2 of x squared dx, the work looks like this. X cubed over 3 from 1 to 2. Plug in the top number, 8/3, minus, plug in the bottom number, 1. Did I say 8 cubed? That was dumb. It was 8/3 minus 1/3, 7/3. But that would be doing this parabola here, from 1 to 2. So I'm doing this area here, and I'm actually getting a perfect area under this curve. If I choose to do integrate from 2 to 1, of x squared dx, you will notice that the antiderivative is still x cubed over 3, but now I'm going from 2 to 1. And if I plug in the top number first, that gives me 1/3 minus the 8/3. That gives me a negative 7/3. Because what we did is we went backwards. So backwards area can be negative. It doesn't seem rational. I know it doesn't. But the formula from A to B implied from left to right. And if you reverse it, you have to realize that the answer becomes negative. Okay? That's the first rule he would want you to know, and it's just a definition of that. Then he has, what is this one? A to A. Well, that's interesting. He says it's 0. Well, same function. If I integrate from 1 to 1 of x squared dx, mathematically, it's x cubed over 3 from 1 to 1. Do you see why it's 0? 1/3 minus 1/3. But what does it look like on the picture? What does it look like in the picture if I'm going from 1 to 1? What does it look like to you? Somebody?
Just a straight line up.
Straight line. And what do you think the area of a straight line is?
It's 0.
It is 0. In geometry, you learned that a point has no dimension and that a line has no dimension either other than length. It doesn't have any width. It's a hair. It's a hair, one hair. What's the area if you put one hair on a piece of paper and tape it down and you want to find the area of hair? I mean, it's so infinitesimally small. Yes, a hair is bigger than what I'm talking about, but even conceptually, it's still 0. What's another rule? Let's see. We've already talked about this one already, how you can pull out a constant out of a sigma notation, remember? Or I'll better not put k, because it might mix you up. I'll go I equals 1 to 5 of x. That k is just a number, like a 3. It's just pulled out. 3 times 1 plus 2 plus 3 plus 4 plus 5. You can pull it out of a sigma. You can pull it out of an integral. Okay? We've talked about that already, I think. Yes, we did somewhere. Antiderivatives chapter. 4.8. We pulled out the number. That was one of the rules of antiderivatives. Sum and difference. And he did say that f and g both were continuous probably somewhere. Let's see. F and g are both integratable, which means they're both continuous from a to b. They're both a to b. So what that implies is, oh, I'm wrong one, a to b. So I can break those apart into 2 integrals, either adding or subtracting, if you wanted to. You don't have to, you can. Okay, check out number 5. This is something like this. You want to do the area, let's see, from A to B. So here's A, here's B, starts here, ends here. That area looks like this. Nice and continuous function, and it's beautiful area. It's the most beautiful area you've ever seen. And I decide, well, no, I want to go more. I want to go over here to C. So I go to C, and there's C up here. And that region looks like this. And it also is beautiful. You need to realize that that area, that the integral, I keep changing the pen, integral from A to B of f of x dx plus the integral from B to C of, it's still the same function, is the same area, if I just did it in one step, A to C of f of x dx. The total is the sum of both parts. Here's the first part, and here's the second part. Altogether, 1 plus 2 is the full thing, so that's the total area. That's number 5. Here's one that you won't get in AP Calculus. It's called the Max Min Inequality. I don't think I've ever used it in ever, because all this is how can I predict the maximum area or the minimum area that it could possibly be? It's this formula that says if you're going from A to B, your minimum of the function, okay, times B minus A, the minimum of the function, the minimum area from B to A has to be less than the integral of f of x. Here's your real answer. That's your real. And then it also has to be less than the maximum area times b minus a. I think we have one example that uses it. You'll never use it in real life. Maybe if I was smarter and I became an engineer instead, maybe I would be using it, but what is the next? 7, domination. I haven't even looked at that one. If one function is bigger than the other function, well, okay. If this function is always greater, I think that would imply this. If this is f, and it goes on, and this is g, it's always bigger. Every value is always above. I think that's what we're talking about. Let's see. If f is greater than g on n interval, so let me cut my a to b to right here. So here's f of a, here's g of a, here's b, f of b and g of b. Then the integral from a to b of f has to be bigger than the integral from a to b of g. Well, that makes sense. Look at it. Here's my area. Let me do the other pen so I can show it to you. Nice and beautiful area from a to b. That area has to be less than all that area. Well, that doesn't, it's obvious that if from a to b of f is bigger than g or vice versa, the bigger function is going to have more area under the curve. Does that make sense? That's called the domination. Wow, how sad. If f of x is greater than 0 from a to b, means that the function is always, here's a, is always a positive number. It's above 0 from a to b. I don't know what happens later. Who knows what happens later before? It could go down to 0 here. Here's c. And before that, it could have been, I'll call that a, b, I'll call that d then. But if that function was bigger than 0 from here, then that means you have to have area. Yeah, of course. And the opposite is also true. If, he didn't bring this up, if your function is always less than 0 from a to b, this area, wait for it, is negative. This area is less than 0, which implies f of x from a to b dx will be less than 0. Under the x-axis, area is negative. Above the x-axis, area is positive. He didn't bring that up in here, did he? No, he did not. Okay, what else? That's enough for that one. Oh, these, I thought I lost the slide, but it's right here. I was just, what I did, these are in your example 1, I think, of the book. He asked to address these issues, and all I did was I superimposed what he was saying on top of his rules. Yeah, okay, so I just talked about them a lot. Here's the pictures of everything. Here is your area of a line, 0. Here is your area under one area, meaning this area is less because from a to b that function was always above. Here is the sum of f plus, what does he have 2? What does he have only, where's g? Oh, f and g, if you add both the areas, it's kind of like this is all of G, all of G. And then this is F. So if you add up that big area with this smaller area, it's going to be more. So the total sum is going to be bigger. Well, that's common sense. Here is from A to B, from B to C, okay, giving you all of it. Here is your minimum being used. I don't know. It looked like somebody was trying to get in, but now they disappeared, so I don't know who it was. They're not there now. Okay. Max and min inequality. The minimum times b minus a, so b minus a is that, whatever that number is. The minimum times b minus a will always be less than the integral of f of x, because here's f of x. F of x is this line here. So your minimum down here is because that's your lowest place of the function, right here. That horizontal line and that rectangle could give you the minimum area. Now you know there's more because you see the picture. There's two pieces of blue above it. If you go to the top of the function and pretend there's a rectangle there, because think about, the whole thing can always be estimated as a rectangle. I mean, a big rectangle. So if you say length times width, this is my b minus a. That's how long that is. And then this is my f of x function right here at this. So the lowest place of f of x, just find the lowest place of the function and draw a rectangle, the same width. That could be the smallest area of that region. Likewise, find the highest place on your function, and from that highest place, draw a rectangle. Then that big rectangle could be the maximum area that my function has. But in reality, the area from a to b of f of x dx will always be bigger or equal to the minimum of the function times b minus a. Because that minimum is this height right here times b minus a. That gives you that small rectangle. And at the same time, the true area of the function will always be bigger than the maximum value of the function times b minus a, because b minus a stays the same, but the height to that piece is bigger than this height. You see that? That height is smaller than the full height. So that rectangle will be more than the actual, because the actual area is only this. That's the actual area under that curve. Obviously, you can tell there's orange above it, so it's less than the maximum guess. But at the same time, I've already used up this whole rectangle, so it's more than the minimum area that it could possibly be. And as I said, I've never really used it because I don't play guessing games. I just want to find the real answer. And nowadays with technology, I mean, I can understand like a long, long time ago, you're looking at some ugly function that nobody knows how to do, you know. I don't know what it's some ugly function in the world. Well, I could say, yes.
I'm sorry. I had a question. So how do you find the minimum?
What's the lowest place on the, how do you find the minimum of anything? F prime of x set equal to 0, and then those are your critical numbers, and you know that's going to be this and this and this and this. Here's undefined, this, and then so that would be my minimum because it would be, that value is lower than all the other extremas, right?
Okay.
So,
So
so I know that the area under that curve has to be less than, I'm going to go to A to B here. It's going to be, if I use that rectangle, that area is less than the total. You can see there's more on top, right? And if I'm playing a guessing game, integrating is very difficult. Integrating from A to B is very hard by hand. Right now we're doing easy functions, but let me tell you, in Calculus BC, you're doing functions that you have nightmares about. So, well, how am I going to integrate it? Well, you got to learn to change these trig functions around. You got to learn to do integration by parts, and you learn how to do all kinds of stuff. And so maybe, hundreds of years ago, the best they could do is say, my actual answer has to be greater than this rectangle. However, at the same time, it has to be less than that rectangle. So all you know is that here's the true answer, and it's bigger or equal to this, and it's bigger, less than to this. Whatever area that was, whatever that area, all you have is a guess. I have a guess at what that integral is. Okay? I don't play guessing games, that's why I don't really care about it that much, but it is kind of interesting. And there's that dominion that obviously if f of x is below or is above this g of x, then the answer above that total area has to be more than that area. Yeah. All right, let's do some problems. Example 2. Illustrate some of the rules. We're going to, here's my problem. I don't know what f is, okay? I do not know what f is. I don't know what h is. He may use g. I don't know what g is, but he at least told me for a fact that if I knew what f was from -1 to 1, the area is 5. If I knew what f was from 1 to 4, it's only a -2. It's less than that one. H, I have no idea what h is, but from -1 to 1, it's actually more than the f. So using those rules, how would I do from 4 to 1 of f? That's 1 to 4. So what's 4 to 1?
Sign? So
Say it again?
Would it be 2?
It would be 2. Exactly. Nice. Now, here I go. I'm going to break this apart because it's too much for me. I'm going to break it using my rules. 2 of, from -1 to 1, of f, plus 3 of, from -1 to 1, of h. So can I use what truths I have up there? What's f from -1 to 1? Is it f, -1 to 1, 5? So that's 2 times 5.
10.
10. Plus -1 to 1 of h is what?
7.
So that would be 3 times 7, or
21.
21, right? Altogether, 31. How about -1 to 4? He broke it up into -1 to 1 from 1 to 4. Okay. -1 to 1 is 5. -1 to 1 of f, yeah. -1, no, it's 1 to 4 is, this is 1 to 4, right? I gotta erase it. I got too much writing on my paper. It's not paper. Only in my virtual dream. Oh, there it is. Okay, that's a -2. So that answer is a 3. And I think I broke those up in slides. Yeah, I did it. And I didn't even use it. All that hard work I did to do the first problem. I was going to do the first problem, then go to the answer. Oh, yeah, it's a 2. And then I was going to do the next problem, whatever I have, and go to the next slide. And I got the second answer. Yay, 31. Then I do the third answer, and I go to the next one. Oh, man, I did all that work for nothing. No thanks either. Nobody cares. Okay, here's a function that, guess what? You couldn't integrate this if you wanted to. Because right now, it's sort of a combination of a chain rule thing. So right now, you don't know how to do this problem, okay? Whenever it's chain rule, looking like if you're doing derivatives. Right now, you don't know how to do that derivative. So we're in trouble. How am I going to integrate this from 0 to 1 if I don't know how to do it by hand? He's asking you, just show that it's less than or equal to the square root of 2. Less than. So he's asking for the minimum. So it's less than or equal to the square root of 2. Maybe that's max. I think he's asking for the max because it could be equal to that. That could be the max. Look at this function and ask yourself, what's the highest value that this could become? You could graph it and say, oh, I know what it is. You could actually use your calculator and get it. Look at this. 1 stays a 1 no matter what. But if x changes, x can be any angle you want. But what's the maximum that cosine can be? Try some numbers. Try 10 degrees, try 30 degrees, try 40 degrees, try 60, try 90, try 100, try 300. Doesn't matter. What's the largest value cosine can ever be? Think of the graph. Say it again.
1.
Thank you very much. The highest, the max, is a 1. So what I'm going to do, the max of this function is 1 plus 1, square root of 2. The max is, it is right there. It's a square root of 2. That function can't be any bigger than square root of 2 because that function alone, so it's a square root of 2 times b minus a, which is square root of 2 times 1 minus 0, which is square root of 2. That is the max. There's your maximum functional value times b minus a. And that's what this is. The maximum that function could be. Let's do the minimum. He didn't ask for it, but we're so good. Minimum of this function times b minus a. What's the smallest the square root of 1 plus cosine of x could be?
0 or yeah,
Okay.
or -1.
What is the Okay, cosine could be a -1. That's right. So what's 1 plus a -1? I think you were right, Claudia. 1 plus a -1 is 0. Square root of 0 is 0. So the minimum of f is 0 times b minus a, which was 1 minus 0, is 0. So even though I don't know how to do this integral, I know that the true integral of the square root of 1 plus cosine of x has to be bigger or equal to 0, but less than or equal to square root of 2. I at least have an idea of what that area is. I just don't know the exact answer. It's between 0 and 1.414. Okay? That's what that's all about. What is he doing here? If f of x is non-negative and it's integratable over a closed interval, ab, then the area under the curve is okay, come on. We already know that this whole thing is about area. We already know that. And there's the answer to that problem. There's the definition of area under a curve. Let's do one, okay? Compute from a to b x dx and I don't know a and I don't know b. So this answer is a and this part is b. That's all I can say. How about geometry? That's a right triangle. 1/2 times the base times the height. That's simple. There's my area. Let's see if I do calculus from 0 2b of f of x, which is x dx. What does that give me? Did I use the right letters? I didn't use the right letter. I just zoomed in. That's not an A and a B. That's a B and a B. Did anybody else notice that? But didn't want to hurt my feelings? Nobody, huh? B squared over 2. Okay. So I'm going from 0 to B of this function y equals to x. Antiderivative, x squared over 2 from 0 to b. Plug in the top number first, b squared over 2, minus, plug in the bottom, 0 squared over 2, still 0, b squared over 2. Got the same answer. Are you surprised that I would get the same answer as a regular triangle in geometry? Should not be a surprise to you. If it's good enough for geometry, then the calculus has to match. Oh, there
Oh,
it is.
so you always have to
Go ahead.
find the antiderivative of the function, right?
Absolutely.
Oh, okay, okay.
Always when I go to a to b of f of x dx is the antiderivative of this
Okay.
from
Mm.
a to b, which means, you know, we're doing plugging in the b, minusing the antiderivative, plugging in the a.
Sir, why didn't we find the antiderivative of the one where it was like 1 plus cosine x?
Oh, because I would give you extra credit if you knew what it was, but it'd be hard. Square root of 1 minus that one?
Yes, I was just wondering, like,
Well,
why?
you're smart enough that you might be able to, with time, figure out the derivative of what is 1 minus cosine of x to the 1/2 power. You might be able to figure it out. I myself, it would take me some work to get there. Tell you what, Claudia, I'll make this to anybody. If anybody can find out what is and send me the message, the first 2 people will get points. It probably is doable, Claudia,
Mhm.
but I didn't know the answer right off the bat.
Oh, okay. Oh, so we didn't need to find it for the last one?
No, I didn't. The whole point for that problem, Claudia, was the fact that maybe we won't be able to figure out what it is. That I don't know the antiderivative. So what I do is I just figured out what the maximum could be, and then I figured out what the minimum was, remember?
Mm-hmm.
So I know that the real answer is between these two. The real answer is between the square root of 2 and 0.
Oh, okay, okay.
I have the a and the b, I just didn't know what the antiderivative was. I'm not saying you can't find it. I just couldn't find it in 30 seconds or less.
Oh, okay, okay.
I may not be able to find it in 30 minutes or less. But if somebody finds it, I will reward them. Let's see. This was the answer we just got. What was going on here? Oh, what if we were integrating from 1 to 2 of a number? He's giving you the secret. But if I was doing it, what's the antiderivative of 3? Derivative of what is 3? Anybody?
3x.
3x from 1 to 2 is 3 times 2 minus 3 times 1, which is 6 minus 3, which the answer is 3. He says, look at, just take your 3 and multiply it by b minus a, 2 minus 1. Wait, did I get it right? Yeah. 2 minus 1 is 3 times 1 gives you 3, the same answer. So it's like if you want to memorize this, then you don't have to do the antiderivative and integrate. You know the answer is going to be b minus a times c. You just know that's going to be the answer. Okay? And this one, yeah, I don't care about this one because I'm not afraid to do x cubed over 3 from a to b, giving me b cubed over 3 minus a cubed over 3. That's not even something I'll think about. This is kind of cool to think about this. Those are just things that people notice. Uh, Look at this y is x. Look at a to b. What if I didn't have that full triangle? What if I was going from 1 to 5? Do you need calculus to get the answer? Anybody? Do I need calculus to get the answer? I've had 3 people talk to me in this class so far today. And I bet you some of you haven't even marked yourself present in the chat. So I'm going to be marking you absent because I never heard you. And I don't see you because I'm teaching off this. I let people in. I don't even know who I let in. All right, for those that are paying attention, no, I don't need calculus. This is a trapezoid. The area of a trapezoid is you take 1/2 times the bases. The bases are the lines that are parallel, and you multiply it by the height. In this case, this is the height of the trapezoid. Here's one of the base, and here's the other base. So without calculus, I could do this problem. 1/2 times a plus b. Well, I gave you 1 and 5. I gave you what I say, 1 to 5. So it is 1 plus b times the height, which in this case is b minus a. So let's do the real answer. 1/2, 3 plus 1 is 4, and b minus a is 3 minus 1 is 2. So the answer should be, without calculus, 4. With calculus, and see, here's the point. You don't always have to do calculus if you can recognize it. But I'm going to do the 1, 2. That wasn't a 3, but I said 5, but I wrote 3, and then I started doing the 3. That's okay. So if I do 1 to 3 of this trapezoid, the formula is this function is y equals to x. The area under that curve is x dx, which turns into x squared over 2 from 1 to 3, which is 3 squared over 2 minus 1 squared over 2, which is 9/2, minus 1/2, which is 8/2, which is 4. Well, what was easier? Was the calculus easier than the geometry? I hope it's not true. I hope you thought the geometry was easier than the calculus, but they got the same answer. How about if y equals to x, you were in the negative? That a, I'm going to just call a negative, this time I'll go -5 for sure, and I'll call this a -2. And there's my function. It's still that function. And so here's the area that I'm talking about. With geometry, you're always going to get a positive answer. But in reality, it's not positive. Well, I think if you use the actual numbers and call this whatever this is, well, that's a -5. That's y equals x, so that height's a -5. That height is a -2. If you use those actual numbers and call that a -5 and call this a -2 and call the height of this trapezoid to be a -5 minus -2 is a -3, I'll bet you any money you'll get a negative answer. But you're not used to using negative numbers in geometry for measurements. So you might get confused by doing area is base 1, that's 1/2, base 1, -5, I don't know what that, yeah, -5, plus base 2 was a -2, times the height, which was, I think I put a -3. times a negative 2. Oh, is it going to give me a positive answer in the geometry? Somebody? No one's talking.
Yes.
It is? It's going to give me positive, right? That's kind of really weird. Because that gives me 14 over 7. That gives me a 7. But the calculus should show integrating from -5 to a negative. Oh, I know why. The geometry doesn't think about the left and right bit. If I switch those numbers around, I'll get a positive number. But if I'm going from left to right, -5 to -2, still the function is x, which still turns into x squared over 2 from -5 to -2. Plug in the top number first. -2 is being squared over 2 minus -5 being squared over 2. Let's see what happens here. Negative 2 over -2 squared is how much? 4. 4 over 2 minus, what's -5 squared?
25.
25 halves. And because that is minus in there, that turns into a -21 halves. How come I didn't get a 21 over there? Did I do some multiplying wrong? 7, 14. Why am I not getting the exact answer? Who can find the mistake? Anybody? Did I do the 5 over here? 5, 2, that's a 7, yeah. Distance was, distance is 3, -3. Yes, I did that. Oh, I didn't put it here. Here it is. You could have had points. Well, no, but I did do, that's a 21 over 2, what I have down here. Oh, good, 21 over 2. But technically it's negative area in calculus because why? It's underneath the x-axis. But you can match it up to the geometry by changing the problem and go from -2 to -5 the other direction, x dx. That will give you the positive 21 over 2 that geometry gave you. But in geometry, you can't differentiate between going left to right. It's just the plain fact. What's the area of that region if you had to buy paint? I still have to buy 21 halves of paint if I need, whatever measurement that is. That's how much square units I have. It's still a positive square units, but because it's underneath the axis, we say in calculus it's negative area. When I paint, my wall, and I have a line here, maybe like where the light switch goes, that would be positive area. That would be negative area. But when you go to the store, if this is blue and this is red, I still got to buy positive gallons of paint. That's just the way it is. What's he doing here? Let me ask you a question. I'm not going to do it because I'm not getting enough people contributing anyway. If I'm going from A to B, will the final answer be positive or negative?
Negative.
Why?
Well, I'm not sure, but maybe because there's more on the negative side.
Well, you can mark that down as that you're pretty sure. Based on the look, based on what this looks like, this is a bigger area than this area, so you got more negative area than positive. So your resultant will be positive area. So good job. Good job. Did I want to talk about this? Not really. Did I want to? Okay, yeah, we do got to do this because we did this already in another lesson. This is the average value that we talked about. Remember that we can take an area that is like weird or whatever, find the area, and then create that rectangular box that has the same area. By basically you're pushing that down and you're finding that line to get this box to be the same area as the total area of the whole thing. So the formula that we'd come up to was 1 over b minus a times that integral. Sometimes books will write it as integrate from a to b of f of x dx divided by b minus a. Same thing. So find the average value of this function from -2 to 2. Okay. I might be able to talk about that area without using calculus. Let me see. Y equals to the square root of 4 minus x squared. Square both sides. Y squared is 4 minus x squared. X squared plus y squared is 4. What is that an equation of? X squared plus y squared is 4. Thanks for asking. Right? It's a circle. It's a circle. You had this in your pre-calc class. It's that circle. And I'm wrong. It's not a 4 by 4. What is it? I'm supposed to take the square root of that. Sorry.
It's 2.
2. Thank you. Is that Claudia?
Yes.
Thank you. You made me happy because you were my student. It's a 2. All right. Circle radius 2 and centered at 0, 0. Because remember, we said x minus 0 squared divided by 2 squared plus y minus 0 squared divided by 2 squared equals to 1. And that was the equation of a circle in conic section. So anyway, what he wants is the average value of this circle. Oh, wait a minute. I just thought of something. I don't think you guys could integrate this one anyway. It jumped out at me as a circle, but it's really a half a circle because he's only going from -2 to 2. So the area from -2 to 2, and plus, it doesn't say plus or minus. It's only plus. So I'm not really using the bottom part of that circle. So that's why. And even if I wanted to, guys, good luck at integrating from -2 to 2 of the square root of 4 minus x. Yeah, somebody might be able to figure it out, what the antiderivative, in other words, the derivative of what with respect to x is 4 minus x to the 1/2 power. Somebody could do it, maybe. But I can't do it in 30 seconds or less. So it'd be better to use the geometry. And I'm doing average value, so I'm going to take that answer and divide it by b minus a. Well, b is 2 minus a -2. That's my a to b, -2 to 2. b minus a is 2 minus -2. That gives me 1/4 of the integral from -2 to 2 of the square root of 4 minus x squared, right? Was x squared? Yes. I don't know why I don't see it here. dx. And since I don't want to do the calculus, I'm lazy. What's the area of a circle? Pi r squared. So that whole circle, if I had it all, would be pi times 2 squared, which is pi times 4 pi. However, I only have half the circle, so it's 2 pi. So this becomes 1/4 of 2 pi, which is pi over 2, is my average value. That means the average area, if I could create that box, I'm just going to pretend, starting from here, making a box, I can find a box that has the area of 2 pi. The area of that box, not 2 pi, is pi over 2. and I can find that line here that gives me the same area. I can actually find that line here, which might be, how big is pi over 2? Somebody calculate it? In numbers, pi over 2? So 1.5 something?
It's 1.5707.
1.5707. I'm just curious, if you times that by 4, by, by, by 4, oh wait, that was pi, right? That's pi over 2? If I times
Yes.
that by 4, what would you get? I'm just curious.
6.28.
That's 2 pi. Oh, that's what I had. That was my area of that half the circle was 2 pi. So that means then this number here is exactly what you said, 1.5707. That number is y equals 2 pi over 2 was how high this is. That's how high that is. And then that's my length. So length times, well, that was a 4, times my height, which is pi over 2, that's my length and width, gave me the same 2 pi, the area of that box, which is the same as the green. So the black area is identical to the green area. And so when you find the average value, you're actually finding out the average y value that gives you the same area. If you could crunch that into a like a Play-Doh into a box, if you could push all that into a rectangle with the same A to B, it's the same area, and you could actually find that line. I think there's an application in physics that does that. Well, at least we're right. There it is. And so what does he say? The average value of f, the average value of the function f is the pi over 2. So when I say average value of the function, the average value of the function is this y value, that pi over 2, that gives me the rectangle. Well, actually, it's got to be the whole rectangle. From that, it has to be that rectangle. It's the y value, that's your average value. It gives the same answer. Same problem. He worked it out with geometry. He didn't show me how to integrate that, so it's like, what? Can't do it either. He did it with geometry. That's it. All right, and I'm missing on my PowerPoint the 2 pages of problems. Do you have it on yours?
Yes.
Okay, you have it on yours. I don't know why I don't have it. How many minutes to spare? Oh, guys, you let me go 5 minutes over?
I don't have an issue with hearing you talk, sir.
You what?
Just say I don't have an issue with hearing you talk, sir.
I didn't know if you stayed. I thought maybe you left, because usually you always help me.
Oh yeah, oh no, because you were explaining the problems. I had no issue with it. I was like, it's okay.
Well, you were there, right? And you were listening?
Yes, sir.
Okay, then I believe you. Thank you for telling me that you